Hello everyone. Welcome back to the reinforcement learning reading club. In this session, we will be reading this paper called "Learning Robust Perceptive Locomotion for Quadrupedal Robots in the Wild," and Zhao will be presenting the paper. He is a PhD candidate in the Aalto Robot Learning Lab at Aalto University. So we can begin.
Yeah, thanks. Hi, I'm Yi. Today I will present the paper named Learning Robust Perceptive Locomotion for Quadrupedal Robots in the Wild. This work is from the Robotic System Lab, ETH Zurich. Yeah, first let's talk about some background. The paper I mentioned here, which is learning quadrupedal locomotion over challenging terrain, is actually the paper from the same lab. To my knowledge, it's the first paper that demonstrates that using reinforcement learning plus sim-to-real agent, we can train a very robust quadrupedal controller that can, let's say, go traverse over challenging terrain with only the perceptive signals, which mean depend only on jolting coders and IMU. And the main technique used in this paper is sim-to-real, which means we first train the agent in the simulator, and then we transfer it to the real robots. Actually, there are lots of impressive real-world demonstration of robotics from just using this technique. There are two keys to make this technique really works. The first thing is that we need realistic simulators. And the second thing is that we really need domain randomization. For domain randomization, you can say that a kind of data augmentation or to a stream, we can consider it that if we train our agent on a large scale of the randomized environment, then the real environment will be just one example of this simulated environment. Yeah, let's jump into the paper. The motivation of this paper is that according to their previous paper, they show that when using the proprioceptive measurements, we can get a very durable and reliable sensor measurement for the legged machine. But the limitation for this method is that, as you can see here, in order to change the gait of the machine, you have to physically fill out the terrain using its leg. So in order to change the height of this leg, you have to first touch the terrain and then adapt it. This will makes you, less energy efficient, and also can influence the speed. On the other hand, if we can use an external perceptive environment, for example, stereo camera or Linda. Let's say we can use it to first perceiving the terrain before making contacts with it. For example, here, let's say before the leg contact with the stair, we can just get sample from this stair, and then we can make a plan and adapt the gait of the machine based on our prediction. However, this measurement is not reliable. For example, when you have the transparent surfaces or the light condition changes, the prediction will not that reliable. So the goal of this paper is that we want both reliable and fast locomotion that can benefit from both proprioceptive measurement and also exteroceptive measurements. The main idea is that if the external perceptive environment are reliable, then we use them. Otherwise, we just back to the reliable, the reliable per perceptive environments. Yeah, I would say that this is just the idea to incorporate these two environments. It's not the idea of this paper. As you can say, I mean, as you can say later, this paper actually includes a lot of stuff, and we will introduce it later. The belief, this is the belief encoder used in the policy. The encoder have 3 inputs, which is the perceptive environment, the external perceptive environment, and also the hidden variable from the previous time step. And then we feed them into our own core, and it will predict the belief of next step and also the hidden state. Instead of directly using this belief state to make the action prediction, we first feed them into the get attention core, which is we make the prediction of whether we're gonna using this external environment based on the prediction of the, let's say, prediction from this belief state. And if let's say if we think that okay, our external perceptive environment are reliable and we're gonna use them, and then we will combine the latent variable get from the external perceptive environment and also the belief state, and combine them together as our final belief state, and then we make the action prediction based on this belief state BT. Yeah, let's quickly go through the training. We're gonna, as I mentioned before, we're gonna train a neural network policy in simulation and then perform their sim to real transfer. There include 3 steps. First is the teacher policy, which means we're gonna train a agent using reinforcement learning, specifically using PPO with privileged information. And then we're gonna train a student policy that we're gonna try to distill this teacher policy back to this student policy without accessing to this privileged information, which makes sense because in real robot, you can't access to this privileged information. And the second step is to deploy our train policy to the real robots, where we're just using their also sim to real transfer. For the training environment, here we use the array sim, which is developed by the sim lab, the robotics system lab. In this environment, we can change the terrain, and I mean it includes different scope and slopes and also steps, and well as different types of stairs. And for the domain randomization, which is the key to make the sim to real really works, which we're gonna include the mass of the robot body and the legs, and also initial jolt position and the velocity, and the initial body orientation and the velocity, and also external forces, and also the friction. Yeah, let's first talk about the teacher policy. The main reason that we need this teacher policy is that if we directly train the policy without accessing to this privileged information, it will be very challenging to train this agent. So let's say first we assume that we can access to this privileged knowledge, and then we just train a reinforcement learning agent to follow a random target velocity command over, let's say, random generated terrain, and that you can see here, and also the random disturbances. For the privileged node information, we mean that nodeless terrain measurements and also ground friction and also turbulences. disturbances. And to train this policy, there include two curricula. The first curriculum is to change the difficulty of the terrain. And the second one is to change the magnitude of the domain randomization and also change the reward function. It will, the core idea is that we want to start from simple and then adapt to difficult cases. For the reward function, the reward function is well-tuned, as you can see here. It includes a lot of well-tuned parameters. But the main goal is that we want to make the robot to follow the command, the target command, without breaking some predefined rules. Yeah, for the training part, I think I don't have much to say. It's quite standard, which is just using PPO. Yeah, with access to the private information, as you can see here. Yeah, and also after we train the reinforcement the teacher policy using reinforcement learning agent, we're gonna map it to this student policy. The most important thing is that we assume that there are no privileged information available at this moment. So in order to make the trained robot, a trained agent to be robust, we add additional noise to the student height samples. As you can see, the input of this student policy include two parts. The first part is the proprioceptive measurement, which is the same as used in the teacher policy. And the second part is the noisy height scan. We fit these two measurements into this student policy, and then we're using this belief encoder to let's say to make the prediction of the hidden state and as well as belief state, and then combined with this belief state as well as the proprioceptive measurement, we're gonna using a MLP core to make the action prediction. The student policy is trained in a supervised way and include two losses. The first loss is the behavior clothing loss, which is quite straightforward because I mean we're gonna make this a student policy to mimic the teacher policy. And the second loss is this reconstruction loss. This might not that straightforward, but it also quite makes sense. The goal is that for mimic this teacher policy, we actually try to first mimic its output, and second, we also want to mimic its input. So as you can see here, we kind of force this learned hidden variable to at least encode some uniform information that can help to reconstruct or predict the to predict the belief state, and this belief state should be similar to what they used in their teacher policy, which is the latent variable get from both external perceptive encoder and also the privilege encoder. So as a result, our reconstruction loss is try to reconstruct both the noiseless height scan and also the privilege information. Yeah, and the third step is for the deployment. Yeah, I don't have much to say about this part. It's just using the zero shoot sim-to-real transfer. They're included two different sensor configuration. The first one is two LiDAR sensors, and the second setting is for real sensors. They're using these sensors to generate elevation maps at 20 Hertz by estimating the robot pose and the point cloud readings. And the policy runs 50 Hertz and samples the height from these elevation maps and combined with its proprioceptive measurement and fit it into the student policy and makes the action prediction. And then we use this. We just using the real robot to execute this predict action command. For the result, actually the result is very impressive. The robot can traverse challenging environment with zero failures, and also they also demonstrate a hike in the RPS with similar duration suggested by a hiking planner. Yeah, I guess maybe I can play a video for a very nice video for this paper. It should be. Yes. Hope. You can say when the let's say when one traverses over the deep snow, where let's say the external measurement is not that reliable because what they sense of the ground is actually not the real ground. So in this case, it will kind of back to the robust or reliable prior measurement to let's say to change the gait of the machine. Yeah, but for the stairs, where we can get the reliable prediction of the from the external perceptive measurement, in this case, we were directly using that plan to achieve high speed. This is the hiking demonstration of this robot. Yeah, this paper is actually a very impressive paper, I would say. Together with their previous work, they show that when using reinforcement learning together with sim-to-real, I mean, we can get a very robust and reliable controller and also as well as very high performance. Yeah, so it's kind of motivates us to continue our research in in reinforcement learning. Yeah, thanks for your attention. If you have a question, feel free to ask.
Hey, yeah, thanks for the information on the paper, because I mean I was actually thinking whether I should join this meeting because I didn't have time to read the paper because of the ICML deadline. But luckily, I mean, we had actually a guy from ETH, this Nikita Rudin, give a talk in one of the formats we have at Darmstadt, and he talked especially about the simulation that they did and stuff like that. And
you
so
mean this simulation?
No, this is why I'm actually now so curious, because here they say, okay, they trained in racing, and there is this paper where they have learning to walk in minutes using, like, basically what they did is they took this Isaac gym simulator and they trained it and with that it allowed them to train, like, I think they used different numbers, but I mean the one that they used, they trained like 4,000 robots in parallel on a GPU. So basically they collected like tons of data each second. But this seemed to be a different training pipeline that they used here, right? So is that like, do you know this other paper? It was at Corl, I think, in 2021.
Did you mean that kind of training, let's say, similar to
exactly this picture that you have there? This is actually this thing which they did on this Isaac Gym on the graphics card.
Yeah,
as far as
exactly.
I know, at least. Yeah,
exactly. Yeah, I remember that they first trained their robots using this simulator, which is, I guess, is developed by themselves.
Yes.
And I guess then later on, I mean, this SX Gym also have the similar training environment. But I don't know whether, but I guess in their paper, they mentioned that they using their own simulator to train this agent.
Okay, yes. Because I was just like, when like this guy from NVIDIA, or like, I mean, he's, I think at ETH, but collaborates a lot with NVIDIA. And when he presented like this stuff, okay, he didn't spend too much time on the policy network. So I was thinking like, which of these details are like also in this probably newer version of them? Because the way he presented it, it sounded like, yeah, you just throw PPO and some neural network on the stuff. And since you have so much data, it's no problem. But like the architecture looks a bit more advanced, particularly with respect to processing the measurements of these depth tensors, right?
Yeah, I guess for PPO training, it's, I mean, yeah, for the architecture, it's for sure it's kind of advanced. But for the, I guess for training, it should be. I mean, I just checked the detail of the policy. They only predict the mean of the. I mean, they're still using a Gaussian distribution and predicts the mean, and for the standard deviation, they're just using a fixed one, I guess.
Yeah. Okay, cool. Yeah, no, because I want to look into that stuff because of, I mean, right, you said it, they used like curricula, and I was thinking maybe you can like regenerate these particular decisions that they did like in an automatic fashion by one of these automatic curriculum RL methods, because it seemed to be, for me, it was interesting, right? I mean, you would think that these kind of myopic tasks that kind of like following a desired velocity target kind of is, right? I mean, like the rewards are pretty instantaneous. You still need this gradual increase or you seem to need, at least, still this gradual increase of complexity. That to me was a bit surprising, actually.
Yeah, I guess if you, I mean, if you didn't use the curriculum learning, it might be harder at the beginning. If you, for example, if you just directly train on some very challenging cases, it might be very easily to fall down. Yeah. Yes. Yeah, but as you said, actually the reward function is quite dense, I would say.
Yeah. And you said they even changed like the magnitude of some of these terms, right? I mean, this sounds pretty crazy, but okay, that's interesting. I need to read into that in more detail.
Yeah. Just strongly study to check their paper. It's
yes.
A very detailed paper, include a lot of details.
Okay, and this is like probably some journal version, right? Then.
Yeah, from journal version.
Okay, cool. Thanks.
Yeah, so are there any other questions? So about this reconstruction loss function. So can you explain the idea again? Was it to reconstruct the hidden states of the recurrent neural network, or was it something else?
Yeah, basically, let's say after this belief encoder, this belief decoder, I mean, using the hidden variable at the input and also the external perceptive measurement at the input, and then they want to predict the estimated privilege information and also the estimated external perceptive information. For example, I mean, in this, for the input of this student policy, the measurement of the height scan is actually quite a noise. They directly, I mean, they inject lots of noise for this for this height scan, for the height samples, and then they just try to using this neural network to, let's say, to kind of you can understand that it's try to denoise the height scan as well as try to retrieve the privileged information.
Yeah.
And this will force that you have a, I mean, it will force the hidden variable have the, let's say, encode some useful information that can make to predict the action here. Yeah, for example, I mean, more detail that in when we train this teacher policy, the input of this MMP core includes the first is the perceptive measurement, and also a latent, let's say, a feature vector that combines first the noiseless height scan or the external perceptive measurement, and also the second part is the privilege information. So we want, I mean, during this student policy training step, we want our belief state can kind of mimic this information used during this teacher policy. Yeah, I guess this is why they're gonna using this reconstruction loss for the, I mean, for the student policy training.
I see. Thanks. Any other questions? Okay, so if not, I want to thank all of you again for attending this session, and thanks to Yi for the interesting presentation. And I wish you a very nice weekend. Bye-bye.
Yeah, thank you so much. Bye.
You too. Thanks, Yi. Bye.
Bye. Bye.